Okay, so let us start with the now the other form of the ODEs like nonlinear ODEs. So before that we have talked about how we can solve the linear system. If it is an homogeneous equation, then that is quite straightforward, and we can look at whether it is in exact form or not, or we can bring down to the exact form, and if not, then if it is non-homogeneous equation, then we basically split it into two component, homogeneous and non-homogeneous, and then try to find out the solution for both, and then the linear combination of the homogeneous and non-homogeneous is going to give the total solution. So, this is what we looked at the example of such a system. Now, we are going to talk about nonlinear system. So, nonlinear ODE, which is like you have an system which is in the form like y plus y prime plus p x equals to y equals to g x y to the power a, where a belongs to R. Now, if a is 0 or 1, then the system becomes linear, then it goes to the linear system. So, to have a nonlinear system, this has to be 0 or 1. Okay. So, that goes to non-linear system. Now, let us say you have a function u x which is y x to the power 1 minus a, then what we can write u prime equals to 1 minus a y to the power minus a dot y prime. So, what we get u prime equals to 1 minus a g y to the power a minus p y. So, this is what we can write g minus p y 1 minus a equals to 1 minus a g minus p u. So, we get u plus 1 minus a p u equals to 1 minus a g. So, that is what we get. Now, u satisfy the linear ODE condition. So, solving this system we can get y equals to the power 1 by 1 minus a. So, that means it has to be some sort of an kind of an variable which we substitute back, and then finally bring down the system where we can get this solution done. Now, here also we will look at an system where this is a y minus b y square. So, we have y prime plus minus a into y equals to minus b y square. So, a here is 2. So, which is definitely not 0 or 1, that means it is non-linear. So, we can do u equals to y to the power 1 by u to the power y to the power 1 minus a, which is 1 by y. So, u prime would be minus 1 by y square prime. So, which if we put it back, we will get minus a by y plus b. So, our u prime is minus a u plus b. So, which in turn one can write this is a u equals to b. So, we get du plus a u minus b dx equals to 0. Given that a is function of x which is given. So, p is q, p is a u minus b, q is 1. So, we can have R, which is R going to be A, and then we can get the integrating factor like f would be e to the power minus a dx, which is e to the power ax. So, if we multiply that, e to the power ax plus a e to the power ax u equals to e to the power ax b, we will have d dx of e to the power x into u e to the power ax into b. So, what that gives us back e to the power ax u ax b by a plus c. And another, this is the non-homogeneous part, and homogeneous part one can write. So, this would be u homogeneous would be c1 e to the power minus ax. Okay. So, what we get like now from here what we get u equals to, so u equals to b by a plus c2 e to the power minus ax, and this is the non-homogeneous solution. So, the total solution would be b by a plus c2 e to the power minus ax plus c1 e to the power minus ax. So, which one can club back and write some sort of an c3 e to the power minus ax, and y is 1 by u, which is 1 by b by a plus c3 e to the power minus ax. Okay. So, now you can put like x equals to t and y t would be 1 by b plus a c3 e to the power minus a t. Then you can plot the system like for t. So, these are the curves which is going to be looking like that. So, this is b by a minus 1, this is y t. So, here y prime is greater than 0 if y less than a by b, y prime is less than 0 if y greater than a by b. So, you get this kind of curve in the solution. Now, this is where it is a first order nonlinear ODE. Now, we can look at the second order ODE, which is for linear. Okay. So, this will give us an system like the y double prime plus p x y prime plus q x y equals to r x. So, this is we straightway taken an example which is non-homogeneous. Okay. And if r x going to be 0, this will lead to homogeneous system. So, as long as this let us say if we multiply it with a function f x, then q x y equals to r x. So, this kind of system also called, or rather remains linear as long as f x not equals to 0. Now, when you go to the homogeneous system, or non-homogeneous system. In this system, this P and Q are called the coefficients. So, let us start with the first, the homogeneous linear second order OD. So, we will take some. So, here we start with some sort of a theoretical understanding, like let us say one theorem where if y1 and y2 both are solutions on an open interval I of equation y double prime plus p x y prime plus q x y equals to 0, then any linear combination C1 y1 plus C2 y2 is also a solution to the system. In particular, y1 plus y2 is a solution to the homogeneous system. Since it is a second order system, it has to have two solutions. So, however, the two obtained solutions have to be linearly independent. Now, we say that if there are y1 and y2 are two solutions, then the linear combination of that is going to be also a solution. We can prove that. How we will look at that? Let us say C1 y1 plus C2 y2 satisfy, or this combination satisfy the system. Then what we will have C1 y1 plus C2 y2 double prime plus Px C1 y1 plus C2 y2 single prime plus Qx C1 y1 plus C2 y2, which is 0. Okay. So, what we get here, C1 y1 double prime plus p y1 prime plus q y1 plus C2 y2 double prime. So, after this you can p y2 prime plus q y2, this is also 0. Now, this equality holds since y1 and y2 are individually solution to the system. So, this will also contribute to, because they would also satisfy the system. So, this theorem only holds true for homogeneous system. Now, these two functions y1 y2 defined on an open interval I call the linearly independent. So, y1 and y2 are linearly independent on I if C1 y1 plus C2 y2 equals to 0 everywhere on I, if and only if C1 equals to 0, C2 equals to 0. Now, assuming both C1 and C2 are not 0, then what we will have, C2 Y2 is 0 everywhere on I. So, we can have Y2 equals to minus C1 by C2 Y1 if C2 not equals to 0. Or Y1 equals to minus C2 Y2 by C1 if C1 not equals to 0. So, either of that case. Now, if Y and Y2 are not linearly independent, then they will be proportional to each other. So, we can define that a pair of solutions of y double prime plus p y prime plus q equals to 0, which is linearly independent on an open interval I, is called a basis of solution of OD on I. So, you see where we are coming from. If they are not linearly independent, then they are going to be proportional to each other. So, that means they are linearly independent, and we define that a pair of solutions of this particular system which are linearly independent on an open interval I, they are called the basis of solution of that OD on I. Now, if Y1 and Y2 are the basis, Y1 and Y2 are basis of the solution of OD on I, y equals to C1 Y1 plus C2 Y2 is called the general solution of the OD in I, and where C1, C2 are constant. When C1 and C2 have absolute value, it gives the particular solution. So, like you can say, if it is given that y of x naught is k naught and y prime x naught is k1, it will actually gives us value for C1 and C2. So, which finally yields that y double prime plus p y prime plus q y equals to 0 and y x naught equals to k naught and y prime x naught equals to k1. So, these are called initial value problem. Okay. So, first of all, either there could be generic solution. So, that means if y and y2 are the solution of this kind of system, which are the basis solution of that OD, then this is called this combination of y1 plus C1 y1 plus C2 y2 would be the generic solution. Or for a particular value, we can find out the particular value of C1 C2, that is called the particular solution, and the system becomes an initial value problem. We can just explore that. We just a simple example, y plus y equals to 0, where given y 0 equals to 3 and y prime 0 equals to half. Here y double prime equals to minus y, so y equals to sin x. So, y double prime equals to minus sin x, which is true. So, the solution would be C1 sin x plus C2 cos x. So, this is y1, this is y2, and y1 by y2 is tan x, which is not constant. So, what we can say, y1 and y2 are linearly independent. So, the general solution would be C1 sin x plus C2 cos x. Now, when we use this value of y rho is 3 and y naught 0 is half, we get C1 equals to half and C2 equals to 3. So, the particular solution would be y equals to half sin x plus 3 cos x. Okay. So, this is the particular. Now, second point is that find out the basis, if one solution is known. So, that means if we know either of y1 or y2, then we can reduce the second order system to a first order system. Like the second order system is given y double prime plus p x y prime plus q x y equals to 0. So, let y1 be a solution in I, then we can y2 would be u y1. So, here y2 prime would be u y1 prime plus u prime y1, y2 double prime would be u double prime y1 plus 2 u prime y1 y prime. Okay. So, if y2 is a solution, now if y2 is a solution, then y2 double prime plus p y2 prime plus q y2 would be also 0. So, if you put it back, u double prime y1 plus u y double prime plus p into u y prime plus u prime y1 plus q u y1 equals to 0. So, which gives us back that u double prime y1 plus u prime to y1 prime plus p y equals to 0. Here y1 is already a solution, so this is going to be 0. Since y1 is solution, plus q y1 equals to 0. So, this means u double prime plus u prime, which is u y prime by y1 plus p equals to 0. Let us say v equals to u prime, then we can write v prime plus v 2 prime by p equals to 0. So, dv by v 2 y1 prime by y1 plus p dx. So, the v would be c1 e to the power minus 2 y1 prime by y1 plus p dx. So, we can write that like this can be written c1 e to the power minus 2 ln y1 minus p dx. So, which we can write 1 by y square e to the power minus p dx. Now, we have v equals to u prime and y2 equals to u y1. So, we get y2 equals to y1 v dx. So, y2 by y1 is not constant. Since u greater than 0, so y1 and y2 are linearly independent, and that form the basis of solution. Now, homogeneous, so here we can see that if we know one solution, we can find out the second solution. Now, there could be this is where we have not talked about P or Q, which are the coefficient P and Q. Now, this could be possible that this second order homogeneous system with P Q constant, then what we can say, y prime, the system would look like that, plus B y equals to 0. Now, since it is homogeneous, then A B is constant, so the solution would be in the form of y equals to e to the power lambda x. Okay. And then we can get an characteristics equation like lambda square plus lambda a plus b, which is where lambda x equals to 0. Now, since e to the power lambda x not equals to 0, this is going to be the lambda square plus lambda a plus b is 0. So, we can find out lambda 1 on 2 would be minus a plus minus a square minus 4b by 2. Now, lambda is decided on discriminant part of a square minus 4b. So, what we can have, that we can have a situation where a square minus 4b greater than 0, then we will get two distinct real roots. Case 2 where this could be 0, then we get one real root. Or third, which is possible, that you can have a square minus 4b which is less than 0, then we will get complex conjugate roots. Okay. Now, this is what you can see. So, first, when P and Q are constant, then this will, the solution would be in this form, and you get this characteristics equation on lambda, and this depends on this a square minus 4b discriminant, and whether it is a positive, 0 or negative, whether we will end up getting real root or one real root or complex conjugate root. So, that would be determined. Now, we can look at the kind of detailed of these different case studies in the next session.